A sloth, a donkey, and a curious human send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
You know, Corn, this whole show runs on GPU compute, and we wouldn't be here without Modal.
Seriously. And that's what powers all our text-to-speech. Everything you're hearing right now.
They're an AI infrastructure platform. Developers use them to run GPU workloads in the cloud with zero infrastructure headaches.
If you're building anything with AI, check them out. Modal.com. If you are trying to build serious agentic AI systems, the no-code tools are a trap. The real power and the real learning happens in the code.
Herman Poppleberry here, and I could not agree more. We're seeing a massive shift right now in early 2026 from what I call prompt engineering to actual agent engineering. The honeymoon phase with simple chatbots is over. People are tired of wrappers that just provide a pretty UI for a single API call.
It really is. People are realizing that a text box that just talks back isn't enough. We want systems that do things, systems that can interact with APIs, manage long-term memory, and recover from their own mistakes without a human holding their hand. But today's prompt from Daniel really hits the nail on the head regarding how you actually get there. He wrote to us saying, "I want to do an episode for someone who wants to learn major agentic AI frameworks like LangGraph, and skip all the no-code stuff to focus on mastering the code that makes agentic AI work. Beyond getting good at Python, what areas would you direct them towards in learning this? What would be a good second and third language? And within Python, what functions would you recommend spending time on?"
That is such a high-value question because the barrier to entry for toy agents is dropping, but the complexity for production systems is skyrocketing. By the way, a quick fun fact before we dive into the deep end, today's episode is actually being powered by Google Gemini 3 Flash.
It is, and it is helping us map out this technical roadmap. So, Herman, Daniel wants to skip the wrappers. He wants the raw mechanics. Where does a developer even start when they want to move past just sending a string to an API and waiting for a response?
You have to start by changing your mental model of what an agent is. In the old days, like 2024, we talked about chains. Step A leads to step B. It was very linear, very fragile. But true agentic AI, the stuff Daniel is asking about with LangGraph, is about state machines. You aren't writing a script, you are designing a graph where the AI is the engine that decides which node to visit next.
Right, and that implies a lot more than just knowing how to write a function. It sounds like you need to understand system architecture. If the LLM is the engine, the developer is the one building the transmission and the steering rack.
Precisely. To master agentic AI, you have to look at agents as distributed systems. One of the first foundational areas I tell people to study is finite state machines, or FSMs. If you look at LangGraph, it is essentially a state machine implemented in Python. You have nodes, which are your functions, and edges, which are the transitions. But the magic is in the conditional logic, the routers. You need to understand how to define a state, how to update that state without breaking the history of the conversation, and how to handle loops.
Loops are the big one, right? Because a simple chain can't correct itself. If the LLM hallucination's in a chain, the whole thing falls over. In a graph, it can loop back and try again. But how does that work in practice? Does the developer write the retry logic, or does the LLM know it failed?
That's the core of the engineering challenge. You usually build a validator node. The agent performs a task, moves to the validator node, and the validator, which might be another LLM or a deterministic code check, decides if the output is acceptable. If not, the edge points back to the original task node with a correction message in the state. You're essentially coding a plan, do, check, act cycle into the graph.
And that brings us to the second pillar, the actor model. This is a concept from concurrent computing where actors are independent entities that communicate via messages. They have their own private state and they fail in isolation. When you start building multi-agent systems where you have a researcher agent talking to a coder agent, you are essentially building an actor system. If the coder agent crashes because of a syntax error, it shouldn't take down the researcher who is still fetching documentation.
Think of it like a professional kitchen. The sous chef doesn't stop chopping onions just because the pastry chef burnt a souffle. They are independent actors. In LangGraph, this is managed through subgraphs. You could have an agent that is itself a node in a larger graph. Mastering this hierarchy is how you build systems that don't just hallucinate into a corner and stop working.
I love that. It makes the agent feel less like a magic brain and more like a microservice. But Daniel also asked about languages. Obviously, Python is the king of the hill for AI, but he asked for a second and third language to give a developer an edge. What is the secret weapon language for an agent engineer?
This might surprise some people, but the second language has to be TypeScript.
TypeScript? Really? I thought you'd say something like C++ for the heavy lifting or Julia for the math. Why TypeScript?
No, because of the full stack reality. Most production agent systems aren't just running in a terminal, they have a front-end component. If you are building a web-based interface where a user is interacting with an agent in real time, you are managing that agent's state in the browser. LangGraph and LangChain have first-class JavaScript and TypeScript support for a reason.
Is it just about the front end, though? Or is there something about the language itself that helps with agents?
It is both. TypeScript's type system is actually often better suited for the complex, nested JSON structures that LLMs spit out. When you are dealing with deeply nested tool calls and structured outputs, having a rigid type system that can validate those objects at compile time is a massive advantage over Python's more flexible type hinting. Plus, if you look at the industry trends in early 2026, the most advanced agentic interfaces are being built with frameworks like Next.js, where the agent logic lives in an edge function written in TypeScript.
That makes sense. It's about where the code actually runs. If you want low latency and a snappy UI, you want that logic close to the user. So TypeScript is the production choice. What about the third language? You mentioned something earlier about high performance.
That is where Rust comes in. Rust is becoming the performance choice for agent orchestration. As these systems get more complex, you aren't just running one agent, you might be running 10,000 concurrent agent sessions. Python's global interpreter lock becomes a massive bottleneck there.
I've heard some people say Rust is overkill for AI because the intelligence is in the model, not the code. If the model takes 2 seconds to respond, does a 10 millisecond savings in the orchestration layer really matter?
It matters when you scale. The intelligence is in the model, but the plumbing is the code. Think about a major AI startup. If they are handling 10,000 concurrent sessions where each session involves multiple tool calls, file I/O, and network requests, they need a language that can handle that concurrency safely and efficiently. Rust's ownership model is perfect for this. There's actually a case study from a startup that moved their agent orchestration layer from Python to Rust and saw a 90% reduction in memory usage and a massive jump in throughput.
That is wild. 10,000 concurrent sessions on a single orchestration layer? How are they even managing the state for that many agents?
They use highly optimized key value stores, and Rust's ability to handle zero-cost abstractions means they can process those state updates without the garbage collection pauses you'd get in Java or the overhead of Python. And there is another angle here, WebAssembly or WASM. As agents become more autonomous, we want them to be able to execute code securely. We don't want to give an LLM raw access to a Python shell on our server. So we compile small tools into WASM modules using Rust.
Oh, that's clever. So the agent can write a solution, but it executes in a totally isolated sandbox.
Microsoft has this project called Wasset that allows agents to execute these modules in a sandbox that is incredibly fast and secure. If you know Rust, you can build the high-performance tools that the agents actually use to do their work. It's about building a secure execution environment for the agent to play in.
So we have Python for the logic and the ecosystem, TypeScript for the interface and the full stack state management, and Rust for the high performance orchestration and secure tool execution. That sounds like a formidable stack for 2026.
It really is. It moves you from being a prompt engineer to being a systems architect. You're building the infrastructure that allows the AI to function safely at scale.
Let's bring it back to Python for a second, because Daniel specifically asked which functions and patterns within Python are critical. If someone already knows basic Python, they can write a loop. They know what a dictionary is. What are the pro-level features they need to master for frameworks like LangGraph?
Number one, without a doubt, is asynchronous programming. You must master the Desinccio library.
I knew you were going to say that. Async is the bane of many beginner developers' existence. Why is it so non-negotiable for agents?
Because agentic workflows are incredibly slow if they are sequential. Imagine an agent that needs to search the web, call a database, and then summarize the results. If you do that synchronously, the agent is just sitting there idling while it waits for the network response from the search engine. In a production system, that is unacceptable. You need to be able to use Tesinccio.gather to run those tool calls in parallel.
And it's not just about speed, right? It's about the feel of the application. If I'm a user, I don't want to wait 30 seconds for a thinking spinner.
Right. If you want to stream the agent's thought process to the user in real time, you need async generators. You need to be able to yield tokens or state updates as they happen, rather than waiting for the entire process to finish. If you don't understand sync awaiting and how the event loop works, you are going to struggle with every major agent framework out there. LangGraph is built on top of an async-first architecture. If you try to run it purely synchronously, you're fighting the framework's design.
Okay, so asyncio is the big one. What else? What about data handling? Because agents are basically just JSON processing machines.
You have to master Pydantic. It has become the industry standard for structured output. When you're building agents, you're constantly telling the LLM, don't just give me text, give me a JSON object that matches this specific schema. Pydantic allows you to define those schemas as Python classes. It handles the validation, the error messaging, and it can even generate the JSON schema that you send to the LLM.
I've seen that in action. It's so much cleaner than trying to parse raw strings with regular expressions. But what happens when the LLM gets the JSON slightly wrong? Does Pydantic just throw an error?
That's where the agentic part comes back in. You catch that Pydantic validation error, pass the error message back into the LLM, and say, hey, you missed a required field here, try again. This is called self-healing code, and you can't build it reliably without a strong validation library like Pydantic. It's the difference between a toy and a tool.
Interesting. So Pydantic is your shield against bad data. What's another deep cut for Python?
I'd point people toward the inspect module. This is how these frameworks work under the hood. When you give a Python function to an agent as a tool, the framework uses dinspect to look at the function's signature, its docstring, and its type hints to automatically build the JSON description that the LLM needs to see. If you understand how tinspect works, you can build your own custom tool decorators and abstractions. You stop being a consumer of LangChain and start being a contributor to the ecosystem.
It's about understanding the magic, so it's not magic anymore. Speaking of magic, what about state management? LangGraph talks a lot about state. How does that look in Python code? Is it just a big global variable?
God, no. Global variables are the enemy of agentic scaling. That is where atyping, type-dictic, and generics come in. LangGraph uses atype-dictic to define the state object that gets passed around the graph. It's a way of saying, this dictionary will always have these specific keys with these specific types. But the secret sauce is how you update that state. You don't just override it, you use reducers.
Reducers? Like in Redux or React? That sounds very front-end heavy for a Python backend.
You define how a new piece of information should be merged into the existing state. For example, if an agent returns a new message, you don't want to delete the whole conversation history. You want to append that message to a list. Understanding how to write these reducer functions using things like operator.add or custom merging logic is the most important part of mastering LangGraph. It ensures that your agent's memory is consistent and predictable.
It sounds like we're moving toward a world where coding for AI is actually just very high-quality software engineering.
That's the epiphany. The better you are at traditional software engineering, concurrency, state management, data validation, the better you will be at building AI agents. The AI part is just one function call in a much larger, more complex system. If your system is buggy, the AI will just find new and creative ways to trigger those bugs.
I think one of the most interesting things Daniel mentioned in his notes was this idea of the framework is the state machine. Can we dig into that? Why is LangGraph winning over the older chain-based approaches like we saw in early LangChain?
It's because the chain model was a lie. Real human workflows aren't linear. If I ask you to write a report, you don't just write it and hand it to me. You might write a draft, realize you're missing data, go back to research, update the draft, check for typos, and then hand it over. That's a graph with loops. It's iterative.
And the old frameworks hated loops. I remember trying to build a loop in early 2024, and it felt like I was trying to build a bicycle out of cooked spaghetti.
They were terrified of them. If you tried to put a loop in a linear chain, you'd end up with infinite recursion or a Stack Overflow. LangGraph treats the agent as a directed acyclic graph or even a cyclic graph where the state is externalized. This means you can checkpoint the state. You can save the entire state of the agent to a database, turn off the server, and then come back a week later and resume the agent right where it left off. That is a game changer for long-running autonomous tasks.
That human-in-the-loop aspect is huge too. If the agent is about to spend $1,000 on an ad campaign, you probably want it to stop and ask for permission. How does the graph handle that pause?
In a graph-based system, that's just another node. The agent reaches the approval node, the state is saved, the execution pauses, and it waits for an external event, a human clicking OK in a dashboard to trigger the next transition. Because the state is persistent, the agent doesn't forget what it was doing. It's like a video game save point.
It's funny, we're talking about all this complex code, but Daniel also mentioned something called the Model Context Protocol, or MCP. He called it the USB port for AI agents. How does that fit into this coding roadmap? Is it something a developer needs to learn alongside Python?
MCP is a new standard from Anthropic that is trying to solve the integration nightmare. Right now, if you want an agent to talk to Slack, you write Slack-specific code. If you want it to talk to Google Drive, you write Drive-specific code. MCP provides a unified protocol so that any tool can be exposed to any agent in a standardized way. It's like how every mouse and keyboard uses USB now instead of those old round PS2 ports.
So if I'm a developer learning this, should I be focusing on building MCP servers, or is that too low level?
Absolutely focus on it. If you can write an MCP server in Python or TypeScript, you've just made your tool available to every major agentic framework. It's the ultimate force multiplier. Instead of building one-off integrations, you're building standardized components. It's the future of how agents will interact with the real world.
This really changes the learning path for a developer. It's not about memorizing prompts anymore. It's about mastering the protocols, the state management, and the concurrency. It feels like we're finally moving away from the magic box phase.
It's about building the nervous system of the agent. The LLM is just the brain, but the brain is useless without a nervous system to connect it to the world and a memory to keep track of what it's doing. If you only focus on the brain, you're just building a philosopher in a jar. If you focus on the nervous system, you're building an employee.
I'm curious about the small models as routers idea too. That feels like a very pro move that moves away from just throwing the most expensive model at every problem. Does that require special code, or is it just another node in the graph?
This is where the engineering really shines. Using GPT-4o or Claude 3.5 Sonnet for every single step in a graph is like using a Ferrari to drive to the mailbox. It's expensive and slow. The pro approach is to use a tiny, lightning-fast model like a Llama 3 8B or even a specialized 1B model as a router. Its only job is to look at the user's input and decide which specialized agent should handle it.
You want a weather report? Go to the weather agent. You want a code reveal? Go to the coder agent. And the router model is essentially just a high-speed traffic cop.
And because that router model is so small, it can run with near zero latency and near zero cost. You save the big guns for the actual reasoning tasks. This kind of architectural thinking is what separates a senior agent engineer from someone who just finished a Hello World AI tutorial. It's about cost efficiency and performance, not just making it work.
It feels like we're finally seeing the engineering put back into AI engineering. It's less about vibes and more about benchmarks, state transitions, and error handling. I think that's why Daniel's question is so timely.
I think that's why Daniel is asking this. He sees the vibes era ending. If you want to build something that a bank or a hospital or a major tech company actually trusts, you have to be able to explain exactly how the state is managed, how the tools are secured, and how the loops are controlled. You can't just say, well, the prompt is really good. You have to show the architecture.
So, if we're looking at a concrete path forward for someone listening, where do they start? You said master async first. What's the hello world of production agents? Is it a weather app? A chatbot?
I would say build a simple LangGraph agent that uses an async generator to stream a response, but give it a memory that persists in a database. Don't just keep it in a Python variable. Use a SQLite database to save the state of the graph after every node.
That forces you to learn how the state is serialized, right? Because you can't just save a Python object directly to disk easily without some thought.
It forces you to learn everything. You have to learn how to define the schema with Pydantic, how to handle the async database calls, how to manage the graph transitions, and how to resume the state. Once you've done that, you cross the chasm from scripting to system design. You've built a persistent, stateful agent.
And then, if you really want to level up, try building a front end for that agent in TypeScript. Don't just use a terminal.
Connect your Python backend to a next.js frontend using a WebSocket. Now you're dealing with real-time streaming state updates across two different languages. You have to manage the optimistic UI on the front end while the agent is thinking on the back end. That is the full stack agent developer blueprint for 2026.
It sounds like a lot of work, but honestly, it sounds a lot more rewarding than just staring at a prompt and hoping the LLM does what you want. You actually have levers to pull when things go wrong.
It's the difference between being a passenger and being the pilot. When you understand the code, you can build guardrails. You can build observability. You can actually see why the agent made a certain decision because you can inspect the state at every step of the graph. You can even build a time travel debugger for your agent.
A time travel debugger? Like, show me what the agent was thinking at step 3 of the loop?
Precisely. Since the state is saved at every node, you can literally rewind the agent's history, change a single value in the state, and see how the agent would have reacted differently. That is impossible with a simple prompt-based system. That is pure engineering power.
I think that observability point is huge. We didn't talk much about it, but if you're building these systems, you need to know when they're failing. You can't just wait for a user to complain.
That's where decorators come in. You can write a custom decorator in Python that wraps every tool call the agent makes. It can log the input, the output, the latency, and the cost. Suddenly, your black box agent becomes a transparent system. You can see, oh, the researcher agent is spending 60% of our budget on redundant Google searches. Let's optimize that node. You're debugging the process, not just the output.
It's just like any other software optimization problem. You find the bottleneck, you instrument the code, and you fix it.
It really is. We're just applying 20 years of software engineering wisdom to this brand new field of agentic AI. The tools are different, but the principles of reliability, scalability, and maintainability are exactly the same.
So, to recap the Daniel roadmap, first, don't just know Python master async UI, Pydantic, and state management via TypeDictic. Understand that a framework like LangGraph is really just a sophisticated state machine. Second, pick up TypeScript for the front end and full stack state coordination. Third, keep an eye on Rust for high performance orchestration and secure code execution via WASM.
And most importantly, stop thinking about prompts and start thinking about graphs. The prompt is just one part of the node. The graph is the application. If you master the graph, you master the agent.
I love that. The prompt is just the metadata of a node. That's going to be the quote of the episode. It really puts the LLM in its place as a component rather than the whole system. It's a very grounded way to look at something that often feels like magic.
It's a powerful component, but a component nonetheless. It's the engine, but you still need the car.
Well, this has been a deep dive. I feel like we've given Daniel and anyone else listening who wants to get their hands dirty a lot to chew on. Before we wrap up, I should probably mention that this whole technical roadmap was brought to you by the folks at Modal. They provide the serverless GPU infrastructure that actually powers the generation of this show.
And if you're building the kind of high concurrency async agent systems we've been talking about, you need the kind of infrastructure that can scale with you. Modal is a great place to run those workloads because it handles the containerization and the scaling automatically.
Thanks as always to our producer, Hilbert Flumingtop, for keeping the gears turning behind the scenes and making sure our own agentic workflows don't crash.
And thanks to Daniel for the prompt. This was a fun one to geek out on. It's nice to talk about the how and not just the what for a change.
If you're finding this roadmap useful, or if you've already started building with LangGraph and have your own pro tips, we'd love to hear from you. Maybe you disagree with the TypeScript recommendation, or you think Rust is too much. Tell us why. You can find us at myweirdprompts.com. We've got the RSS feed there and all the ways to subscribe.
We're also on Spotify and Apple Podcasts, so if you're enjoying the show, a quick review really helps us out. It helps other developers find this technical content in a sea of AI hype.
One last thought before we go. As we move deeper into 2026, do you think we'll see a standard language for agents emerge, or will it always be this multi-language dance? Is there a Swift for agents on the horizon?
I think the dance is here to stay. Python for the research and the core logic, TypeScript for the user interface, and Rust for the infrastructure. It's the holy trinity of modern AI engineering. Each language does one thing perfectly, and agents need all three.
The Holy Trinity. I like that. Well, this has been My Weird Prompts. I'm Korn.
And I'm Herman Poppleberry.
We'll see you in the next one.
Goodbye.
This episode was produced using Google Gemini 3 Flash. Text-to-speech by Chatterbox.
Thanks for listening to our show, My Weird Prompts, where our thoughts go from slow takes to facts on cue. We change and follow through. My weird prompts.